Hello, welcome to the channel Microwave Testing. Today we will learn what the mouse system is. In the last video we have learned about a further method of non-destructive testing which uses radio waves or microwaves. It was the NMR, the nuclear magnetic resonance technique. Normally, NMR systems are very bulky and stationary, especially its medical variety MRT. Today we will learn about a mobile NMR system called mouse and its applications to cultural heritage. Maria Bias will explain this to us again.
Mobile nuclear magnetic resonance. What do you think of when you hear the term mobile NMR? We've seen in a previous video that NMR experiments are done in large superconducting magnets like this one. So then what does mobile NMR mean? Does it mean that whenever we need to do experiments in a remote location like an archaeological site, we would take this kind of huge magnets that weigh several tons with us to the remote location? If you want to find out the answer, stick around and you will learn exactly what mobile NMR is. Hi and welcome back to my channel, and if you're new here, I'm Maria and I make videos related to cultural heritage and heritage science. In today's video, we'll learn about mobile NMR, what it is, how it works, and in the end, we'll see some applications of mobile NMR in the field of cultural heritage. So let's start by understanding what mobile NMR means, because it definitely doesn't mean that we take these huge superconducting magnets to different locations where we want to acquire the NMR experiments. In a previous video, we've learned the basic principles of NMR, and we've seen that in order for us to acquire NMR experiments, we need magnets to create the magnetic field in which we examine the sample, and we also need radio frequency coils which send radio frequency pulses to the sample. There, we've learned how the magnetic field is created by superconducting coils, and those magnetic fields are quite high. Presently, they go up to about 28 Tesla. For comparison, the Earth's magnetic field is about 1 million times smaller than that, and the magnetic field that's used for MRIs in hospital is around 1 to 3 Tesla. In mobile NMR, instead of using large superconducting magnets, we use permanent magnets to create the magnetic field. The magnetic field created by these magnets is a low magnetic field, and it's also an inhomogeneous magnetic field. And here's what a mobile NMR system looks like. I'll show as example a mobile NMR system called the NMR mouse. And by mouse, I don't mean this kind of mouse. Regardless of how cute he is, we can't use him as an NMR magnet. But mouse comes from Mobile Universal Surface Explorer. Now let's have a look at the schematic representation of this system. In this case, the magnetic field is created by a combination of permanent magnets, shown here in black. On top of the magnet, we add the radio frequency coil. This coil sends the radio frequency pulses into the sample, the same as the RF coil does in high-field NMR. The difference here is that now the coil is a surface coil. And because of that, it's easier to bring the magnet close to the surface of the object we want to examine without the need to remove a piece of the object to place it inside the coil to run the experiments. This is great for cultural heritage because it means we can acquire NMR experiments non-invasively, so we don't damage precious objects of cultural heritage. This ability of running the NMR experiments on the surface of the object is why mobile NMR is also called unilateral NMR or single-sided NMR. We bring the sensor close to the object, and the region where we acquire the NMR experiments is called the sensitive volume. This region is at a certain depth within the sample, and it varies depending on the magnet characteristics. This region can be at a distance somewhere between around 2 millimeters to around 2.5 centimeters from the sensor. And this is what the NMR mouse looks like in action. Here you can see the magnet, the black cube that's close to the painting, and it is connected to the other electronics which we need in order to run the experiments, and that in turn is connected to a computer. And here's a closer look at the magnet. You see that the magnet is really close to the painting, such that the surface coil, which sends the radio frequency pulses, is parallel to the surface of the painting. Now that we've seen the kind of magnets that we use in mobile NMR, let's have a look at some of the NMR experiments that we can acquire in low magnetic fields using the NMR mouse. We can measure relaxation. And by relaxation, I don't mean this kind of relaxation, though this is a pretty nice way to end a full day of running NMR experiments. By relaxation, I actually mean NMR relaxation. We've learned the basic principles of NMR in a previous video, which I will link in the top right corner and in the video description if you want to watch it later. There, we've seen how the spins align in the presence of an external magnetic field. And when we apply radio frequency pulses to the sample, the spins flip. And after we stopped applying the radio frequency pulses, the magnetization will return to equilibrium, moving from a perpendicular alignment to the magnetic field back to its parallel alignment to the external magnetic field. And this return of magnetization back to its equilibrium state is called T1 relaxation, or longitudinal relaxation, or spin lattice relaxation. We can follow the magnetization vector shown here in orange as it returns back to equilibrium in time. And this can be a slower process or a faster process, shown here by the two different build-up curves. How fast this is happening depends on the kind of sample we measure. By feeding these curves with exponential functions, we can identify the exact value of the longitudinal relaxation time in different samples. There is another type of relaxation called T2 relaxation, or transverse relaxation, or spin-spin relaxation. Here we're back to the moment right after the application of the RF pulses. Now the spins are in the transverse plane. And for simplicity, we'll keep only the arrows so that we can see what these spins do in the transverse plane after the application of the RF pulses. And now we'll monitor the evolution in time of the transverse relaxation as the orange arrow. Just as they move into the transverse plane, the spins are in phase. But in time, they start dephasing. And as they dephase, you can see that the transverse magnetization, the orange arrow, decreases. And then the spins dephase more, and the transverse magnetization decreases more. And it decreases even more with more dephasing of the spins. Finally, here's the evolution of the transverse magnetization in time. And this decrease of the transverse magnetization in time can be slower or faster depending on the type of sample we're measuring. And by feeding these curves with exponential functions, we can find out the values of the transverse relaxation time in different samples. But besides feeding the T2 decays with exponential functions to obtain the T2 values, we can also do a different kind of analysis on the T2 decay curves. We can integrate the first region of the T2 decay, and that will give us the proton density. That's a value that's proportional to the amount of hydrogen atoms that are present in that region of the sample where we acquire the T2 experiment. And by measuring these T2 experiments and extracting the proton density at different depths within a sample, we can record depth profiles of the sample. This is an example of a depth profile. Here, the signal intensity is shown as function of the depth in the sample. Each point here represents the proton density at a certain depth, which we've seen that we can obtain from the T2 measurements at that depth. And by analyzing these kinds of depth profiles, we can identify different regions in the sample that have different proton densities. Here you can see these regions highlighted in blue, orange, and green. And this gives us the stratigraphy of the sample. For example, when analyzing the stratigraphy of an oil painting, we can discriminate between the different paint layers and the canvas. But how do we get the NMR measurements at different depths? We can place the magnet in a positioning system that allows us to move the sensor with respect to the sample. In this schematic representation of the profile NMR mouse, the magnet is placed on a moving table, which allows us to move the magnet up or down as indicated by the white arrows. And the sample is fixed on the top table of the positioning system. Because the sample is fixed, we can move the table down, and that moves down the magnet, and at the same time it moves down the sensitive volume where we measure in the sample. Here we move the table down again, and you see that the magnet and the sensitive volume moved down as well. And we moved down again, and the sensitive volume where we acquire experiments changed again. This way, we can acquire experiments at different depths within a sample. But the sample doesn't have to be fixed on top of the magnet. We can rotate the whole positioning system with the magnet such that if the sample is vertical, like for example in the case of wall paintings, we can bring the magnet close to the sample from a lateral position. And now, to acquire experiments at different depths, we just have to move the magnet left and right with respect to the sample. Mobile NMR has so many applications in the field of cultural heritage. It can be used to study the stratigraphy of paintings, to study the treatments and aging of the materials that made up the paintings. It can be used to monitor water penetration in wall paintings, which we know is a factor that leads to their deterioration. It can also be used to study ancient mummies and bones, and old paper and parchments, and even musical instruments. In the future, we will talk about all of these different case studies, and we will see how mobile NMR can be used to study such a large variety of cultural heritage items. I hope you enjoyed learning about mobile NMR and its many applications in the field of cultural heritage. If you like the NMR mouse, please give this video a thumbs up, subscribe, and hit the bell button for more fun videos from the world of cultural heritage and heritage science. And before you leave, I have a question for you. If you could study any object or site of cultural heritage using mobile NMR, where in the world would you take this magnet for experiments, and which kind of sample would you want to analyze? Let me know your answers in the comments below this video. Thank you for watching, and I'll see you next time. Bye!
That's it for today. Thank you for watching. See you next time. Goodbye.